Can you move your speaker? All right. Um, Hello, the two of you. Today we're doing chores. This is like the final boss. So like, yeah, just bear with me. I'm gonna try and go slow because it is a very heavy algorithm. But again, just like please stop me at any time if there's anything. Um, yeah. And also because there's so much, I'm probably not gonna go over the review of last time. Like, are you guys comfortable with that? Like the review of like bits versus qubits and stuff like that. Oh yeah, there's 408 slides, so okay. Were you what was the last one you were here? How long ago? I missed the review. The Grover's one? Okay. I mean, it should be fine. You don't really need to know Grover's to know this. But I mean, it's in here if you want to look at it. So let's go down a lot. So, thank you. Oh, the slides are kind of messed up, but it's fine. There's like a weird white space at the bottom. Okay. All right. So the overarching problem, this isn't Shor's problem yet, but the overarching problem is that we want to factor or find prime factorizations of numbers. Uh, So yeah, exactly. So here's an example. You have some large number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And here's its prime factorization. Uh, so 2 is a prime, 3 is a prime, 3 squared, 5 prime, and then these two large numbers. Good on that. Also good on prime numbers. Yeah, that it basically means that you can't like decompose it any farther. So it's like this can't be like a multiple. These can't be a uh, product of two other non-trivial numbers. Yeah, and then here's like a tree diagram to show that. So this number can be represented as 2 times this number, and then this 617 million can be 5 times this like 123 million, and then this 123 million is 9 times this, and then you eventually hit like the leaves of the tree, and then that's your prime factorization. Good. Divided by two, still dying. Huh? Because this is like 1 billion. It's like 1.2 billion. So like half of it's around. Find this number with 10 unique digits by two, you get that number with nine. Well, because it's like this is like 1.2 billion. So then if you divide it by two, it's like just around 600 million. Oh, I don't know. It's a funny number. Well, I mean, these together make 10. Yeah. So when you divide this by 10, you just get rid of the zero. Okay. All right. Off track. Yeah. So large numbers like those used in cryptography, like RSA, there's no classical like way to find this in a reasonable amount of time. That's why like your data is safe cryptography stuff. Anyway, so the problem is you're given some integer n. It'll always be in red from now on, so that you remember that it's the number we're trying to find the prime factor of. And just say you happen to know some factor d. It could either be prime or not. Um, then the prime factorization of n is like this recursive formula. It's like the prime factorization of the factor, and then times the prime factorization of the original number divided by that factor. And here's that in a tree. So like if your n is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and then your d is this 2, for example, uh, then the prime factorization of this number is the prime factorization of 2, which just ends up being 2, and then times the prime factorization of this number. So it's like a recursive formula. Um, okay. Yeah, again, you just keep recursing, and then your base case is when the number hits a prime. So I think I have that again here. Yeah. So like here D1 is if it's a prime, then the prime factorization of it is itself, and then this can split even more if a factor of this n over D1 is some D2. So I think I have another tree diagram. So this is n, d1 is this, the prime factorization is itself. Prime factorization of this number is this d2, prime factorization, prime factorize that, and then you prime factorize this, so you just keep going. Make sense? Okay. Yeah. And then what Shor's algorithm does is find these single factors d. They could either be prime or not prime. But then to solve the prime factorization problem, you just chug it into this recursive formula where you just do division, where you just divide the number by d and then do recursive prime factorization calls. Yeah. Again, find one of these factors d, and then you can split the number n into two factors b and c, and then n equals b and c. One of the factors is d, and then the other one is n over d. So then you just do recursive calls. Good. Okay. Yeah. And then you can test, and then you can keep testing to see. So testing if a number is prime, there's some classical algorithms to do that that are efficient. By efficient, we just mean this is a. Oh, okay. Uh, it went the power button.
They've been in other club meetings that tried to register the projector does turn on at 6:15 and refuses to turn back. It's like a tape to the projector.
Oh my god.
That's something I have to volume.
There's no speaker. Yeah, please mute me.
Is that?
Hello? Okay. Still don't even have a. Okay. Anyways, so testing if a number is prime, there's classical algorithms to do that. This AKS one is like definite, and then this Miller-Robin one is like randomized. Anyways, and then so when you reach the base case, then you found a prime factor. Then you can't split the prime number anymore. Yeah. It's kind of- uh, I think that is. Uh, yeah. So if we do one of these classical tests, if a number is prime, then we can plug into the recursive formula and keep going. So everything besides Shor, or so like doing like this recursive formula outside of Shor's is not quantum. It's classical. Um, yeah. Eventually you hit the base case, find a prime factorization. And you're also not guaranteed to succeed Shor's algorithm, similar to Grover's algorithm. Uh, and no Shor's doesn't just take n as some bit string and then output the factor d. It actually does. It's a hybrid algorithm, so it'll do some quantum part and then it'll do some classical post processing or even pre processing, and then the quantum part has the speed up. Yeah, so it's not quantumly finding the factor d; it's quantumly doing something else and then doing something classically to find the factor d. So obviously the question is, what is it doing quantumly? And Shor had two main insights when developing the algorithm. The first one is that this factoring problem can be reduced to a different problem called order finding, and then that's what we can do quantumly. Yeah, Peter. Okay. Okay, yeah. So the definition of this order finding, this reduced like problem, it'll seem very random, but we'll show like that it actually will help you find the factor. Um, yeah, so we're gonna do some classical stuff before we do order finding. That's the classical like pre-processing. Then we'll do order finding, quantum, and then we'll do some classical post-processing to find the factor. Um, oh yeah.
Like guaranteed to work like as Grover's algorithm? Did you say like why I'm guaranteed to work in like the Grover?
Yeah. So in Grover's we discussed that you could measure and get like a wrong result, and then you would just try again. And it's the same thing here. You could get a wrong result and you just tried. Yeah. Okay, so this is the reduction from factoring to order finding. So you just choose a random number called a between 2 and then n minus 1. We just don't include 1 and n because they become trivial. So it'll be in blue from now on so that you know it's that random number. Um, you can check if you got lucky, and if you already found a factor, then you're done. But like that's like almost never gonna happen, especially when n is large. Um, so it's called Euclid's algorithm, or yeah,
Whatever that.
yeah, it's a very efficient algorithm. Yeah, it's all classical. So you can check if you have a factor by checking this GCD. So for example, if you find the GCD of 14 and 35, it's 7 because if you take 7 and divide, or if you take 14 and divide it by 7 and take 35 divided by 7, you both get integers. So 7, you can say that 7 divides both of these numbers, and thus it's a factor of 35. And here is an example of when it wouldn't work. GCD of 3 and 16 is 1 because there's no integer that's greater than 1 that you can divide 3 and 15 or 3 and 16 by it and still get an integer. So that's inconclusive about the factors of 16. Yeah, again, yeah, like you said, Euclid's algorithm and it's logarithmic. So yeah. So anytime we think we have a candidate for a factor, we can easily test it classically. Okay, if we don't get lucky, which will be most of the time, we need to find this order, which we said, which is the order of A mod n, which we denote by just this order subscript n and then of A. And then we'll define that right now.
Power to the 8 1.
Yeah, yeah. So the order of n so the order of A mod n is the smallest integer n, such that when you take that random number A, raise it to that order R, you get 1 equivalent to 1 when you do mod n. So here's just an example to make that clear. Order of 2 mod 21 is 6 because 2 to the first power is 2, which is equivalent to 2 when you do mod 21. And then 2 to the second is 4, which is equivalent to 4 mod 21. These three lines just mean equivalent. So it's like when we're taking mod 21. 2 cubed, 8, which is also 8 mod 21. 2 to the 4th, 16. 16. And then 2 to the 5th is 32. But then when you take mod 21, you basically subtract 21 from 32. And then you get 11. And then 2 to the 6th, which we claimed as the order, because when you take 2 to the 6th, you get 64. Then when you do mod 21, you get 1 because 64 minus 3 times 21 is 1. So it's like you can remove 3 copies of 21 like from 64 pretty much. Are you guys good on like modular arithmetic? Okay. Um Okay, yeah. So you are guaranteed to get 1 because we did the GCD test before. You don't have to worry about the group stuff, but it seems kind of random, right? Like we're trying to find a factor, but now we're computing this order. So let's discuss why we're actually doing this and how it helps us find the order. Yeah, we want to find a factor of n, right? So if this is the definition of order, that random number a to the power of the order is 1. If you just subtract 1 from both sides, you get a to the r minus 1 is equivalent to 0. And then we're just going to say let r be even. I don't discuss this later, despite what I say. I forgot to. But the probability of r being even, there's like some conjecture or something that is greater than 3/4. There's some proofs about it, but we'll just say that it's even. Yeah, there's some proofs about it, but yeah. So if a to the r minus 1 is equivalent to 0, let's take a to the r minus 1. We can factor this as this. So if you think of this as like 1 squared, you can think of it as like a difference of squares. So it's like a to the r over 2 squared minus 1 squared. And then you can plug into your difference of squares formula, and then you end up getting this. If it doesn't make clear sense, just believe it for now. Honestly, there's a lot of things you're gonna have to just believe me on. So let this be the first one. So you can factor this number, and then that'll be equivalent to 0 mod n. And what does that mean? If so, as a general thing in modular arithmetic, if some integer is equivalent to 0 mod n, then that means that n divides that number k. And then in other words, that means that that k is equal to n times some integer because, like, again, if you take, well, I mean, yeah, that's just like how you do mod. That's like the definition of modular arithmetic. Uh, so yeah. Are we clear on like why that's the case? If something equals 0 modulus something, then it's that number times an integer. Okay. Yeah, here's that definition again. So we're going to use this now. If this factor polynomial is equal to 0 or equivalent to 0 mod n, then that thing is equal to some integer times that n. I forgot to make the n red, but yeah. Um, Yeah. So let's just say that the prime factorization of n is just this product of primes. So p1 through pm is just a prime number, and then k1 through km are just the powers of those prime numbers. So that means when you multiply them all together, you get n. So that'll be this n right here. So let's just plug it. So those three different cases that we'll analyze. The first one is that that prime factorization of n is completely saturated in the first factor, which is the a to the r over 2 minus 1. So the a to the r over 2 has all the factors, and then the other one just has some constant, and then that's what you get, right? Does that kind of make sense? So it's like, where are the prime factors in that like product of the two polynomials? Okay. Let me put out the three cases so that you can contrast them. But the second case is the exact opposite, that the prime factorization is in the other one, the a to the r over 2 plus 1. So the a over r, or a to the r over 2 plus 1 has all the prime factors, and the other one's just some constant. And then the third case is that the prime factorization is split. So the first factor has some constant times some of the primes, and then the second factor has some other constant times the other primes. Um, does that make sense? The three cases we're considering? Okay. Um, okay, here's case one, that the prime factorization's in the first factor. Yeah, so we're just gonna simplify it, remove those alpha betas. Let's just say everything's in the first, and this is a constant, and then it's equal to a constant. It's informal, but the argument kind of still holds. So actually, we say that this is not possible because if we just ignore this because it's a constant, has no primes, it would imply that the factor where all the primes are is these constants are different. Some other constant times n, but that would mean that by the definition we used before, that a to the r over 2 minus 1 is equivalent to 0 mod n because it's equal to some constant times n. And then if we just add 1 on both sides, we're going to get this equation. So looking at this equation, can someone tell me why this is not possible? Yeah, exactly. So this r over 2 is less than r, but then the definition of the order says that r is the smallest integer such that a to the r is equivalent to 1. So we can't go any smaller. Okay. Yeah. Does that make sense? So case one can't happen. So that's good. Um, okay, case two is that the prime factorization is in the other factor. We don't get the same thing. This could happen, and if it does happen, we just ditch that choice of A and then choose a different one. So that's a case where I guess you could say it fails, where you choose an A. So so you're gonna do some tests with the order that we'll go over, and then if that fails, then you're like, okay, it had to have been because it was case two. Yeah. Yeah, the reason as to why the case is bad is because it doesn't tell you anything. If we use the same logic as before, it implies that a to the r over 2 plus 1 is just some constant times the n, and that doesn't help us find the factors of n because we get like the same number back pretty much, like times some constant. So it's like we're trying to find the same prime factorization because all the factors are in here again. So it's like we've multiplied the original number we were trying to find the prime factorization of, by some constant. So it's like there's no point. And then we're trying to find the prime factorization of that. Is that a little clear? Yeah. Sorry if I feel like I'm going fast, but if feel free to stop me. Huh? Sure. Uh, okay. Third case is the case we want. Some prime factors are in the first factor, some prime factors are in the second factor. Yeah. So we found two numbers that split the prime factors of n instead of containing all. So we can actually just compute the GCD of this number here, which will be guaranteed to not be a like trivial one or n, because those will be the other two cases, and then we'll actually get our factor. Um, yeah. Uh, skip these. Uh, okay, let's just go to the.
Does that part make sense? Like,
It's like
maybe on that side.
yeah, it's like case three is what we want. That the prime factors are split because it doesn't like saturate all the factors into something else.
You just take this GCD.
Yeah, you literally once you know the order, you just take this GCD, and then if that GCD is greater than one, then that's your factor.
Before the R actually.
Yes, yeah, exactly. So Shores will find the order R. That's pretty much what it does. This is just like classical stuff before there's no quantum yet. Yeah,
If I'm assuming if they all get
yeah. Questions on Zoom, if there's any. Okay, for the people or person that just joined, pretty much we're just going over like the classical pre-processing that happens before Shor's algorithm. So we actually haven't dove into any quantum stuff. And the goal of Shor, like just to give a high level summary, the goal of Shor's algorithm is to find a factor of some number n or of some number n. Yeah. Did we post the slides? Oh, okay. We probably should do that. If you want, you can do that. I don't know. Okay. We'll post the slides like right now. Yeah. Um, okay, here's the pseudocode for the function. So you pass in some number n, and oh yeah, actually I glossed over this. Before finding the order, we can actually classically and efficiently test if n is like a prime power, so just like a single prime to a power. That you can do that efficiently classically. We don't go into detail of that, but that would eliminate the need of order finding. So it's like we've already found a prime factorization if that's the case. That's actually the first thing we test in the pseudocode. If n is some power of a prime, that's it. Then you return that prime, and that's the, or actually it should be like p to the k. That's your prime factorization. Actually, no, it shouldn't. That's your prime factorization. You got lucky again. Second line in the code is you just keep repeating. What you're repeating is choosing A's. So uh, again, A is a random integer. This should actually be 2. This should actually be n minus 1. Slide should be posted, by the way, now. So you pick up that random integer A. You test if you got lucky, test if you already found a factor. We discussed that. Huh? What? Oh, because the A is supposed to actually be between like two. Oh, okay, yeah, that is true. Yeah. Okay, if we, yeah, ignore that then. Okay, if we didn't get lucky, then we have to find the order, and that's what Shores will do in quantum lead. That's not a word, by the way. Um, yeah, if R, if the order R is odd, yeah, if the order R is odd, then we said like we just continue because then we can divide it by 2 and get an integer. Um, if it's even, we compute these two factors that we just discussed. And then literally all we do is, okay, actually first we test if the second factor is 0 mod n. That would mean we're in case 2. That would mean all the factors are in that number. Then we continue and choose another A. If not, literally all we do is just compute the GCD of this with n, and if it's greater than 1, then that's the fact. So I think I walked through an example. Yeah. So let's say the number we want to factor is 21. We pick randomly that a equals 10, and then the order of 21, or the order of 10 mod 21 is 6, because 10 to the 6 is 100 or 1 million, which is equivalent to 1 mod 21. You can check on that. Yeah. Uh, and then all we do is compute this factor, a to the r over 2, which is 10 to the 10 cubed minus 1. Oh yeah, r is even as well, so that's something to know. 10 to the 10 cubed minus 1, which is 12 mod 21. And then this one is 14. Oh, I think it goes straight into pseudocode, but basically this is greater than 1, so the GCD, the factor ends up being GCD of 12 and then 21, or 21, which is 3. I think that goes, yeah, okay. Here's it in the pseudocode. So you start with n equals 21. Yeah. You test if it's a prime, and the prime is greater and the power is greater than 2. This is not the case, so we're not lucky, unfortunately. Then you pick a random integer. Let's say that integer is 10. You test the GCD if we already found a factor. The GCD is 1, so we haven't got lucky and found a factor already. Then we find the order. We just said that the order is 6. We'll go over how to find that with Shor's algorithm. Yeah, that's the definition of order. If R is odd, then we continue. R is indeed even, so we're not going to choose another A. Then we compute this first factor, which is 10 cubed minus 1, which is equivalent to 12 mod 21. Compute the second factor, which is 14, like we just stated. And then we check if the second factor is equivalent to 0 mod n. Not the case. So that's good. We didn't run into case 2. Then we find the GCD of F1. Actually, this mod n does not need to be there, but it makes this look nicer. Then you find the GCD of that F1 with n, and that ends up being 3, and then that's your factor. Yeah, because it's greater than 1. Does that example make sense?
Wait, no. This is like that we use for
What was that? So R is 6, but then for these factors, you divide it by 2 in the power.
fifth. Why do you do that?
Here?
You have like one mod 21.
Uh, Here? Right here? Oh, this is just a definition of order. So the order definition of order is that a to the r is equivalent to 1 mod n. So this is before you do any division, but this is before you divide it by 2 or anything. We're just saying that 10 to the 6 is equivalent to 1 mod 21. That's a definition of order. Yeah. Okay. I think that's it for order. Yeah. Okay. That's it for the reduction. So that was the reduction that factoring reduces to order finding. So now we're going to go over quantum order finding. It's not magical, yeah. This is the quantum part of Schrod's algorithm. So let's formally define the problem. You have an integer n and an integer a between 1 and n, and then you know it satisfies GCD of a and n is equal to 1 because you didn't get lucky. And the output is the order R, and here's the definition of the order. I'm just gonna like keep repeating it so you just like remember it eventually. Yeah. I said Short had 2 insights. The second insight was that this order problem in its classical definition is more or less equivalent to yet another problem that we can solve quantumly called phase estimation. And I say more or less because it has more classical processing around it. So let's go to this next problem. So we're going to show the equivalence between order finding to phase estimation. So the first thing is, let's just review what a period is. Huh? What? No. Mathematically. Okay. So the period of a function is just the time or like it actually doesn't have to be time. It takes for something to repeat. So mathematically, it means that if you take any point of a function and then you add its period, you'll get the same exact value. Can anyone think of an example of a periodic function? Sine, sure. Then, uh, And there you go, there's sine. Sine is periodic. Sine's period is 2 pi because if you take any point, like this blue point, you add 2 pi, you'll get the exact same thing. You take this green point, which is at x equals pi, you add 2 pi, you get the same thing. You take this purple point, I don't even know what that is. You add 2 pi, you will get the same thing. So that's the period. Make sense? What does this have to do with order finding or phase estimation? Well, here's the definition of order. Here's the so yeah, we'll get to that. So here's the definition of order once again. Hopefully you remember it now. Um, yeah. So let's define this random function where we take for f of x is a to the x mod n. We can actually say that the period of this function is r because if we take f of x plus r, which is our proposed period, we get a to the x plus r mod n. Let's split this. Let's split the exponent. We get a to the x times a to the r mod n. We know that a to the r is equivalent to 1 mod n because that's the definition of order. And we get the same exact f of x back. So f of x plus r is equal to f of x, which means the period of the function is r, the order. Does that make sense? Good. Um, yeah. So let's find a new algorithm called period finding, where it takes in any function f and it outputs the period of that function. Simple as that. Yeah. And that was basically and if we input that function that we defined, then we solve the order finding problem. So that was just the motivation of defining the f in that way. Yeah. So let's focus on that now. This is our function. The naive way would just be to take some unitary or some gate or u, and then you input some at x, and then you output that function. But that's not reversible because yeah, exactly. So it's not like 1-to-1. So you can have different numbers that when you take a to the x mod n, you get the same exact thing. So like if you're just given the output of a function, you don't know what the input is. So I won't go too much into detail on that, but does that like make sense at a high level? Okay, so what do we do instead? We implement this, I just noted as MA, and if you multiply, but you'll call it the multiplication or something like that. Multiplication by A, you can think of it as. So just times A. So if you put some ket into it, it'll multiply it by A. It'll also mod n it. So it's a little different, but we can make some observations. M squared on X is MA applied on MA. MA we just said is this right here. And then we apply MA once again, and then you get A squared, right? And then let's just generalize that. M to the K is just A to the K times X mod. Huh?
Yes.
Yeah, I mean that's like too far into the weeds, but yeah. Yeah, here's just an example if that didn't make sense. Here, if we take M2, so A is 2, and then we input the binary representation of 11, you'll get 7 because A is 2 here, and then X is, let's just say it's 11, but in binary. So 2 times 11 is 22, which is 7 mod 15. That's why we get the binary representation of 7. Make sense? Good. Here's that definition again. And let's just observe if we input y equals 1, or actually I actually changed x to y, so just be wary of that because another x is going to show up. So if we just put this ket to be 1, then we actually implement the function that we said was periodic with period r. Yeah. So makes sense? Oh yeah, we take it to the x power because we want a to the x. Yeah. And then second observation, if we input k equals r, so the power of that thing, then what do we get? We get a to the r times y, but what's a to the r? What's a to the r?
1.
Yeah, it's 1, because a to the r is the order of a mod n. Yeah. Well, because we have this mod n, it's 1, yeah. So then we just get y back. So this MR is the identity matrix. So the next thing we're going to do is find the eigenvectors of MA, which, if you're not familiar, is if you take some operator, we'll call it U, and then you input some vector to it, what you get is the same vector with some constant in front. But the main deal is that the eigenvector, so just call it constant lowercase u. That means that this is an eigenvector. So more concretely, when we want to find the eigenvectors of MA, I'm going to use this space that's there for some reason. When we want to find the eigenvectors of MA, we're finding some psi that satisfies some constant that satisfies this equation. When you take MA, you multiply it by psi, you get some constant times the psi back. And we'll go over why this is important for the big picture. Okay, this is the eigenvector, and I'm going to skip the proof, but this is the expression of the eigenvector. It's a uniform superposition of these a to the j's, so it's like a, so it'll be some sum of like a, or actually 1, so constant plus 1 plus constant times a plus constant times a squared plus constant times a cubed, and then all the way to a to the r minus 1. So that's like the form. Do I expand it? Let's see. Yeah, yeah, I will. Also, we define this or this omega r, which is just actually I'm gonna just like this notation is gonna be consistent around the whole thing. Anytime you use omega and then subscript, it's gonna be equal to e to the 2 pi I and then over that subscript. So, and also the complex number is just a part of like what makes it, like complex numbers will allow these vectors to be normalized. We'll actually go over that when we define phase estimation, but for now, like in quantum in general, complex numbers exist and you just treat them like regular numbers. They're like, because your states live in a complex space. So yeah. Okay. Okay, here's the expansion. Like I said, sum a1 plus a squared. And then these coefficients are these omega r's with some powers with the numbers. What was that? Yeah, that would be how you prove it. But yeah, I mean that I don't use that specifically in this proof, but you could do that as well. And then also these cats are mod n, but we're almost exclusively going to be working mod n from now on, so I'm going to drop it. So it'll make things a lot cleaner. Yeah, there's other eigenvectors, but these are the ones we care about for sure. Here's the proof that I'm gonna skip. And let's see. There's like a okay. Okay, here. Okay, this is the algebraic proof. Clearly you don't want to see that. So here's just like a little small visual proof. Remember that the eigenvector is a sum of this like of 1, a squared, a cubed, all the way to a to the r minus 1, right? When we take MA and then multiply it on that thing, it's going to be MA and then times like that sum that I was saying, plus boom A plus all the way to, yeah, a to the r minus 1. So when we apply MA onto this thing, what MA does to each state is, remember, it's the multiplication by A. So to this 1, it'll multiply 1 by A. It'll take this A, it'll multiply it by A, so you'll get A squared. When you multiply it by up to AR, you're going to get 8. Minus 1. When you multiply it by A, you're going to get A to the R. What do we know about A to the R? A to the R is 1. So it basically goes back to where we started. So if I erase this, let me see if I can move it. Okay. So it's like if we start as a sum of all of these, and then we multiply by ma, we're basically just going to the next one, just adding another power of a. And then when we apply that on the last vector, a to the r minus 1, we're going to get to a to the r, but then a to the r is the order, so then we get that 1 back. So that's like at a high level what we're doing in the proof. So does that make sense?
So that means A is okay. There's that work from all the way.
Only so a is not equal to 1, but a to the r is equal to 1, equivalent to 1, because everything in the ket is mod n, like we said. Yeah. Questions on that? And if you're interested in the actual proof, then slides are. Okay, so we're labeling the eigenvectors as psi k. These are the eigenvectors we just found. And what we find is that the constant in front of the eigenvector that we get in front is called the eigenvalue. What we find is that it's e to the 2 pi I k over r. Okay, where r is the order and k is this subscript right here. It just labels the kth eigenvector pretty much. There's r minus 1 eigenvectors. So so this is the equation of the eigenvector. Now we can define what quantum phase estimation is and show that it's equivalent to order finding classically. So here's the input to quantum phase estimation is a unitary u and one of its eigenvectors, psi k, and then the corresponding eigenvalue is of this form to the e to the 2 pi I theta k, and then theta k is some real number between 0 and 1. And in other words, you have this eigenvalue equation. And the output of the function is just the theta k. And the reason why we define the eigenvector to have this complex exponential form is because our eigenvalue should be normalized. So at the end here, when we take the norm squared, e to the 2 pi I theta k of psi k, then, okay, there should be one bar. But yeah, this will end up being 1 because this coefficient, if you take the complex conjugate and then multiply it by itself, you're always going to get 1. So that's why that's like a general form. Are we like good on that? Like any refreshers on complex conjugates or anything? Okay, so we'll just take that. We'll just take that for granted. Like this is the definition of phase estimation. You have some operator or some unitary, we call it, and then we want to output some information about the eigenvalue. And actually, this theta k we call the phase. So we're estimating that it's literally in the name. Like we're estimating the phase. We're not going to get it exactly. We'll show why that's the case. Yeah. So before we implement quantum phase estimation quantumly, let's just go over how we use this in Shor's, because remember I said that order finding is somehow related to quantum phase estimation. So let's show how they're related. Yeah, we're gonna pass MA as our unitary into quantum phase estimation, QPE.
Right now.
You forgot what?
Wait, are slides posted somewhere?
Yeah, they're in the Discord. Yeah, remember the goal of quantum phase estimation is to somehow get the order R. Shor somehow made that connection. So the eigenvalues of MA, as we just determined, are this, right? If we pass this in to quantum phase estimation, remember the form of the eigenvalue is 2 pi I theta k, right? But then the eigenvalue of MA is e to the 2 pi I k over R. So when we output theta k for quantum phase estimation, we're actually going to output k over R. What's R? R is the order, right? So it's like the order is there somewhere when we do quantum phase estimation. Yeah, so we would read in k over R an approximation because phase estimation. And then somehow we'll use classical post-processing to get R from this k over R. K is actually like, we'll go over what k is as well, but it's like related to what eigenvector we have. Is that good? How we're using quantum phase estimation to get the order? Yeah. So remember in quantum phase estimation, we output, so we have some we have some unitary, and then we pass in an eigenvector, and then the eigenvalue is of this form, right? And then the output of quantum phase estimation is this theta k, right? But then that MA operator that we realized had something to do with the period and whatever, that had some stuff to do with the order. And then we found the eigenvectors of that. And then we found that the eigenvalues of that are this, e to the 2 pi I k over r, right? So if we just ran quantum phase estimation using this MA as our input, and then this psi r as our eigenvector, we would output k over r. Does that make sense? By quantum phase estimation. And k over r has the order in it, r. So we do some classical stuff and then get r, the order. And then remember again, we use the order to find the factor. Good. Okay. Yeah. Ideal case, if we had psi 1, then k over r would just be 1 over r, and then it's really easy to get r from that, right? And then you just reciprocate that value and you get r. So you might ask, like, why don't we just use psi 1 then? And let's show why. Uh, the definition of our eigenvectors looks like this. We showed that, but there's something lingering there, and it's actually the order r. So it's like we're trying to find the order r, but then if we wanted to pass psi 1, we would need to know the order r in order to prepare that state. So it's like we can't do that, right? So yeah, that's what I say down here. Psi k has r in it, yet we're trying to get the order r. So we can't just prepare the state and pass it into phase estimation. So to remedy this, we're going to make the following observation about the r minus 1 eigenvectors that we found. What we're going to do is take a uniform sum over all those eigenvectors. So 1 over root r means uniform, so it'll be normalized at the end. And then all we do is just sum all of the, actually r eigenvectors, not r minus 1. Make sense? And then I'm going to skip this, but if you do some algebra on that, and you use some geometric series, you will find that the uniform sum of all eigenvectors is just the one state. And while we can't prepare individual psi k's, we can definitely prepare this one state, right? So that's what I'll discuss next. So we can't prepare individual eigenvectors psi k, but somehow a uniform superposition of them is the one state, which we can indeed prepare. So we have MA on 1 is equivalent to MA, and then on this uniform superposition of eigenvectors. We just showed that these are equivalent. So, right? So this is indeed valid. And then by linearity of the operator, you can take this MR, put it into the sum, and they'll act individual on these eigenvectors. What do we know about these eigenvectors now? We know the eigenvalue equation that we said before. So yeah, we just sub in the eigenvalue times the original vector, right? And yeah, that's so the observation here is that when we pass MA and then 1 as our state into phase estimation, after we do our measurement, we're gonna phase estimation will basically be performed in superposition on all of the psi k or eigenvectors. And then at the end, when we do measurement, we're gonna get a random k over r, or yeah, for some random k over r, and each will have uniform probability because we prepared a uniform superposition. So it's like you'll read k over r, and then random k, which is between 0 and r minus 1. Does that argument make sense? It's like ideally, if we could prepare like psi 1, then we would just do that, but we can't because psi 1 has r in it. So we're like, if we sum all the eigenvectors, we somehow get 1. So we're just going to pass 1. But then the consequence of that is that we don't know which eigenvalue we're reading because we passed in r different eigenvectors. Does that make sense?
reading. Like, why is that? Like, we're just getting a quarter of our.
Correct.
Not that we're just getting.
So, okay, so it is because imagine you do quantum. Okay, so let's imagine you magically prepare side one. You pass in a quantum phase estimation and you read, let's say in base 10, you read 3.1568, right? Now you know what R is. It's 1 over that, right? Because 1 over R is R, right? But then if I gave you the same thing and I said this is K over R for some random K, now do you know what R is? Right? Yeah, exactly. So that's a trick, right? It's like you don't know what K is, so this number is like almost random to you. It's like if you knew what K is, that'd be great, but you don't. Yeah. Yeah, exactly. Okay, good. And perfect segue into the next part is how do we extract R from the approximation of K to the R? And again, K is random, and we read some binary representation. That's basically what I was saying here. We use a classical algorithm. This is not quantum anymore. I'm gonna skip the algorithm for now, and then maybe when we're done, if we have time, we'll come back to it. I don't think we'll have time, but yeah, there's some way to get R, some classical algorithm to get R, and I think I might be wrong, but I think the complexity is like n to the sixth. So it's actually kind of slow, but it's polynomial. Yeah, we're getting to the quantum part. That's why it's like yeah. It is actually a pretty easy algorithm to understand, so I would recommend going over the slides if you have time. But yeah, this is like the algorithm. It's like these you can see like these continued fractions pretty much. Um, yeah. This is the continued fraction stuff still. So we're gonna get to the quantum stuff. That's why we're skipping it for now. Yeah. Yeah. It's 7.
Why is it so long?
Because I wanted to make sure it was easy to read. Okay, this is still continued. Okay. All right. So far in Shor's algorithm, we said that prime factorization is the big problem here. It's like we want to factor or find prime factorizations of large numbers. Prime factorization uses Shor algorithm, which will find single factors. Next, Shor's first insight was that finding single factors reduces to an order finding problem. Again, here's the order finding problem. A to the R is equivalent to 1.
Like the time you like gone through all this stuff on solving it, it's completely different problems. Forgot what you were.
Yeah, that's why I'm like recapping. It's like you probably forgot. Okay, so once we know the order of A mod n, then we propose that this GCD is our factor. We went over why that's the case. Shor's second insight was that classical order finding is more or less equivalent to quantum phase estimation, which we went over. Here's the problem statement again. You're given a unitary U and an eigenvector, and you know the eigenvalue, and you want to return that phase in the eigenvalue. Good. Yeah. And then what we do with phase estimation is we use the unitary MA, which is multiplication by A, and then the eigenvector, it's actually not an eigenvector, but we pass in the one state anyways, which is the sum of eigenvectors, and it will perform phase estimation and superposition. And then after we do that, we measure a close approximation for K over R for some unknown K, and then we extract the order R from that using this classical algorithm called continued fractions. So that's how we get the order R. So from here, we can take that R and then know that's the order, and then we propose our factor. So does that make sense? The big picture? Okay, good. Okay, let's do some quantum stuff. Yeah. So now we want to actually implement phase estimation as a quantum circuit. So here's the problem again. Now I'm going to start coloring the parameters to make them easier to understand. Can you see that green? So unitary U in purple and an eigenstate or eigenvector psi in blue. And then the eigenvalue is either 2 pi theta, theta is a real number, and the output theta is in green because we want to output theta, so it's like good. Um, okay, yeah, I kind of explained this before, but the eigenvalues look like this because we want our states to be normalized. So the most general like eigenvalue that is normalized is e to the I theta. And then the 2 pi is just like it makes the math with shores specifically, or like with phase estimation specifically, a little easier. But you could define the problem where you ignore the 2 pi and then like the 2 pi is just absorbed into the theta. Yeah. Yeah. So note what we're doing next is a general phase estimation problem. It's used in Shor's algorithm, but it's also used in other algorithms. So we're not using anything specific to Shor's right now. So ignore that. From that eigenvalue, e to the 2 pi theta, we're going to let theta be a finite binary decimal. So the way we define that is that theta, remember we said theta is between 0 and 1. So it's 0 point, and then m bits represented in base 2. And then each bit is either a 0 or 1. And then we're going to have m bits. So something to note about this is that this is not always true about theta. Oh, okay, wait. Okay, first an example. So if m equals 2, and then we had the first decimal, or the first bit as 0, and the second bit as 1, and 0 dot J1, J2 is 0.01 representing base 2. And are we comfortable with like binary to like base 10 expansions? So it's like you take this number and you multiply it by 2 to the negative 1. You take this number, you multiply 2 to the negative 2. So it's similar to like a regular binary number. So it's like so like this is a binary number, and then you want to convert it to base 10, you would do 1 times 2 to the 1, or 2 to the 0, plus 0 times 2 to the 1, plus 1 times 2 to the second, etc. Right? So it's just that, but we're on the other side of the decimal, so we use negative in our exponents. So does that make sense? So that's binary to base 10. So when we do that conversion, you get 1 over 4 represented base 10. So 0.01 represented base 2 was 1 over 4 in base 10. Good. And then we're assuming that form of our theta, that it's some m-bit binary decimal. Good. Zoom good. Okay. Yeah. What I was saying before is that theta is not always, so we truncated theta at m bits of precision. In general, theta could be literally any real number. It could be irrational for all we know. So in general, it is an infinite decimal, but we're truncating at m bits because we only have so many qubits. Because at the end, we're going to input m qubits into phase estimation. At the end, we're going to measure those m qubits, and that's going to be this number right here. So it's like if we had infinite qubits, I'm sure, but like we only have so many. So m is like almost like a parameter in the phase estimation. It's like how precise do you want your answer to be? Does that make sense? I'll just note that. Precision. Um, yes. Uh, yeah, it's not noted. Um, yeah, this is what I just said. We truncate theta at m decimals of precision. We're going to input m qubits into quantum phase estimation. When we measure theta at the end, we're going to have an m-bit approximation of it. So the m we choose is related to how accurate our result is. Now let's take our theta, rewrite it in base 10. So like I was just saying, it's J1 times 2 to the negative 1 plus J2 times 2 to the negative 2, all the way to Jm times 2 to the negative n. And then this subscript 10 means in base 10. So like what we use every day. And then base 2 is binary. let's do some math on this. So this 2 to the negative m, let's factor it out. 1 over 2 to the m is equal to 2 to the negative m. So then we get this, right? We just take out 2 to the negative m from each factor. We'll go over why we're doing it. But, and then, yeah, let's make another observation. This is just J1 to JM in base 2, but like not on the other side of the decimal. So it's like, yeah, it's like now this is like greater than 1, but then before this is like less than 1 because there's a 0 dot in front. So all we've done is converted this like on the right hand of the 0 of the decimal to the left hand of the 0 by just dividing by this 2 to that. So good on that. These slides take forever to load. And then let's just call this string of J1 to JM just J. So yeah, J is just J1 to JM. And then in base 10, that's going to be some number from 0 all the way to 2 to the m minus 1 because now our number is greater than 1. Yeah. Good. Okay. Now let's solve phase estimation. I'm just going to throw the circuit and then we're going to prove it. That's the easiest way to do it. So here's the circuit. It may look similar to some stuff we've done before, and in ways it doesn't. So this is the circuit, and that V in the middle does this. Huh? Yeah, we'll go over that. Last thing. So V will take is a 2-qubit or is a like a 2-register gate? Huh? Yeah, yeah, quantum Fourier transform. Yes, you did. So V will take in some number K. That'll be multi-qubits. It'll be some number in binary. And then it'll also take in another state phi. What it'll do is it'll keep the first register the same as K, but then the second register, it'll multiply U K times to it. So this K in the first register determines how many times we multiply U. So does that like make sense what V is doing? So that K in the front doesn't actually change, but it determines how many times you multiply U on the second register. And then we'll go over why you need that. Yeah, and it's called modular explanation, modular exponentiation. And QFT is the quantum Fourier transform, and we'll mention that later in the circuit. Yeah, and let's just contrast this to previously, like the Deutsch-Delta algorithm, for example. So in the Deutsch-Delta algorithm, the first thing we do is apply a layer of Hadamard against superposition. We're still doing that right here. And then the second thing we do is apply our oracle, which encodes some information about the input in superposition. And then 3, we apply Hadamards again to undo the superposition. Here, this V indeed does encode some information about the input because our input is U. That's why I colored it. So it's like you remember that's an input. So U is an input. So V does something with the input to the problem. But then this last thing is different. This QFT is different than like Hadamards at the end. So yeah. Yeah, somehow the inverse QFT extracts our answer from the superposition. Yeah. Okay, let's label our states. These are our states, side 0, side 1, side 2, side 3. Let's calculate what they are. Side 0, we haven't done anything. It's just the same as the inputs, 0, m times. Remember, m is how precise we want our answer to be at the end, because at the end we measure those m. So this is an m qubit register, remember. It's not 1 qubit, it's m qubits. And then the second one is some psi. That's also multi-qubit. That's not 1 qubit. Psi 1, we apply a Hadamard layer on the first qubit, which is this equal superposition. Do we remember the equal superposition thing from before? So all it's saying is that we go through every m bit string, and then we sum them up uniformly by this normalization factor. Do you remember that? And in the case that m equals 2, we get what we've seen, this like canonical like plus state, right? That's when m equals 2. Um, also, if you want me to pause so you can write stuff down, just let me know. Okay, let's just shift the parentheses. We're allowed to do that. Let's take the parentheses and put them inside the sum. Sure. Okay, psi 2, we take our psi 1, we apply v on that big state, right? What does that do? By linearity, we can throw the v into the sum. It'll be v on k and then psi. So v is a 2-qubit gate, so now we need to sub in the definition of v. We said that v will keep this k register the same, and then multiply u k times onto that psi, which is psi is our eigenvector. So this is where the magic comes in. So psi is our eigenvector of u, remember? And so if u times psi is equal to e to the 2 pi I theta psi, then u to the k on psi. Yeah, yeah. So u to the k on psi will be that same eigenvalue, but k times. Because every time we apply k, we add a new eigenvalue. So we just keep adding powers. And then by just like laws of exponents, you can multiply that k in. So that's where this k comes in. Let me know when you want to move on. Yeah. Yeah, Zoom looks fine. Good, guys. Okay. All right, let's just continue for the sake of time. But okay. Here's that repeated again. Psi 2 is that state that we just determined after applying UK times. Okay. Remember we said that theta is j over 2m, 2 to the m for some j, right? J is like that bit string that we said, where j is like j1, j2 to jm represented in base 2, and then over 2m because we moved the thing from like the right side of the decimal to the left side of the decimal. So all we're doing is subbing that in, and I'm changing theta, or I'm changing j to be green now because j is like directly related to theta. So it's still what we want to output at the end of the function. So theta and j are like very related. Um, Next thing we're doing, remember I said the omegas would come back. So omega subscript 2 to the m is e to the 2 pi I over what's in the subscript, which is 2 to the m here, and then j times k. So basically we're just absorbing this factor that will just keep carrying on so we don't have to keep rewriting it. So we're just calling it that. But the j and k we're keeping because we're going to be manipulating the j and k. And also, if you guys forget like what each variable is, like feel free to remind me, and I can remind you like what it is, like K or J, or like yeah, we're gonna have a lot of I, J, K, whatever. Yeah. Yeah. Okay. Now let's move this stuff out. So let's isolate our eigenvector. So all we're doing is just moving the coefficient and the ket out, which we're perfectly allowed to do, and then we're gonna define this weird state where it's like a uniform superposition, but with these like weird like constants in front, we're going to find it as phi of j, phi subscript j. So it's indexed by like that j. And then the second register is the psi eigenvector. Yeah, here's that again. Same state. We're defining this as this. Okay. Now we're recalling again that theta is j over m. So we said that it's this, and then we like did some shifting, and then we found that it's j over 2m. So yeah, this is what I was saying before. Once we know j, we know theta. Because we know what m is, we know what q to the power of m. So now we want to extract j from quantum phase estimation. and then we'll just find theta from that. Yeah. Okay. So if our state right here, this register is phi of j, and then we want to read j at the end, this q of t somehow needs to get you j at the end. So q of t will map from phi j to j, and then we'll measure, we get j. So that's the objective of q of t. Make sense? Okay. Okay. Two things left to do. How do we implement that v that like we just like subbed its definition? It's like that's not really like adequate enough. And then the second thing is obviously the q of t. Yeah, and what is q of t? Um, let's go. Let's backtrack a little and let's implement this v. Did I skip this? Okay. Okay, let's implement that v like oracle that we said. So here's its definition. We multiply u on the second register, amount of times it's dictated by the number of the first register. Yeah, k is a m-bit number, so m, and that's the same m that measures how precise we are with our theta. Um, okay, okay. Okay, here. So let's say k is 14. So this is 14 in binary. So we input 14, that takes 7 qubits. We output, well, it doesn't take 7 qubits, but let's just say m is 7. We're measuring theta with m bits of precision. And then at the end, it's going to be unchanged. So this is still k. But then this register has changed to having u applied 14 times because this number is 14. Good. So it's just like a black box version of it. And then here's the general case, like some number k, you apply it k times. And then this is just k in base 2. Okay, expanding it in base 10 again. This is just taking the coefficients, multiplying them by the 2 to the power, and then decreasing the power. Um, okay. Okay, let's just do some. Okay, skip. Okay. Okay, I'm gonna have you guys answer this question. So let's just say you plug this definition, you do some algebra, k will stay the same, but then you end up getting this weird result where you have u, like many applications of u. The first one is u to the 2 to the m minus 1, and then with a k1 in the exponent, that's just from manipulation, and then all the way down to u to the km. So remember that those inputs are define your number k, so they're either 0 or 1. So if your input is a 1, then you're going to apply. So let's just say for some general ki, if you're okay, sure, you answer the question. But if the input is k, if the input is 1, then we're going to apply this gate. If it's 0, then we're not going to apply the gate. So yeah, exactly. Does that make sense?
Yeah.
Yeah, it's like the whether we apply the operation is dictated by the value of k. So uh yeah, control whatever you said. So okay, here's that. So this v operation is this. So this first factor is controlled due to the 2 to the m minus 1 on register k1 because of that. And then each factor is just a different control. In gate 4 or in gates, it would look like this. You apply just those control gates down there, and that'll implement your v. So sorry if that was like fast, but it does make like when you do the algebraic manipulations, it does end up making sense. Okay, good. Questions on that? This is a good slide to just like stare at and just like understand that it's like that it works. Yeah. Okay. Okay, Q of T is next. Yeah, Q of T. Now that we implement V, we can get ourselves to this side 2 point. Now Q of T needs to map this to J. Remember that? Good. Yeah. Again, or Q of T dagger actually. Q of T, regular Q of T will get you from J to this. It'll be the other way. How do we implement Q of t? Then we can if we know Q of t, then we can implement Q of t inverse. So we're just going to focus on Q of t. Again, nothing to do with Shor's, just general Q. Other algorithms use Q of t as well. Okay, here's the general expression. This is our, what we said is phi j. Okay, let's take this k parameter and put its by. We're going to do this a lot, by the way. It's base 10 form.
Specifically J to that expression we thought.
Wait, what?
Specifically J to
Yes. Q of t is j to this.
Not the perfect expression to
yes.
use this operator.
Exactly. Yeah.
How do you think of it?
I don't know. That's why he's famous. Okay. Let's expand k into its base 10 form, like we said. Okay, k is going to be blue now. Remember, k is our sum index, so just n bit or m bit strings. God, these slides take so long to load. Okay, so all we're doing is subbing that in, right here. And then I'm just going to expand the k register as its bits, as its m bits, and then here it's its base 2. Just doing that. That's perfectly fine. Okay, so this becomes an iterated sum because if you remember a, or sort of like, if we did like omega to the a plus b, it would be omega a times omega b. So this, oh wait, no, we're actually not doing it. Sorry, we're not doing that. All we're doing is focusing on this sum. K, so each bit k is going to take on 0, 1, and it's always going to hit 0, 1. So what we're going to do is split this sum right here into these m different sums. And they're only going to go between 0 and 1 because they're only focusing on one bit. So instead of all the bits changing in one sum, we're just changing one bit at a time. And that's perfectly fine. We're still going to go through all the bits. So in a loose sense, does that make sense? I know it looks intimidating, but yeah. Okay. Now we're going to use the exponent property where it was so small I had to decrease the size. But if you have like omega to the a plus b, it would be omega to the a times omega to the b. So all we're doing is taking these factors and then putting them into their respective sums because this has a k1 in it, so we want it to go into the k1 sum, right? So we're just like conveniently separating it. And then these end up being tensor product states because these are tensor products right here. Like these are implicit tensor products, k1, tensor, all the way to km. Does that make sense? Like you don't have to fully understand the math right now, but just like general, we'll just do it. Should I just skip this? This.
Hurts my brain all the right way.
Okay, we'll just skip. So we're doing some analysis. Feel free to read up on it. If you stare at it for like 20 minutes, it should make sense. So literally all we're doing here is simplifying the right-hand side of Q of t. So that state that we got that we called psi 2, we're just simplifying that into a different form. So let's show you what we get. Okay.
I don't want perfect.
Don't. Okay, here. So remember this. Oh wait, no, this is not the same. Okay, maybe I'll just keep going. Okay, what have we found? So what we found, which we didn't find, but this state at the end of Q of t, we've simplified to these product of Q's, and then these Q's are defined as this right here. So whatever that is. So all we've done is simplify the right hand side of Q of t, and I'll show you what we do with that specifically. So yeah. Okay, yeah, sure. So if we take this side of Q of t and expand into its binary form, so remember that's just a binary number, so it's m bit binary number, and then this is an m bit or m qubit. Both of these are m qubit binary numbers. So if J1 to Jm maps to Q1 to Qm, then that means individual J alpha maps to Q alpha. So yeah, here's just a picture of that. K1 to Km, they individually map to those Qs that we just showed before. Um, now, so now the question we have to answer is what gets us from J alpha to Q alpha, and then here's the expansion of Q alpha. So we're going to do some more simplifying of Q alpha that I'm going to skip. Okay. Uh, okay. Here's a very similar question. So Q alpha, we simplify to this expression where we have a product of things with these J's on top. Remember the bits of J are estimation of theta. Remember theta is J over M or J over 2 to the M. And then J, the bits of J are these green. That's why they're green, right? It's like what we want to get out. So the bits of J are either 0 or 1. Again, so for each bit JL, we add this phase, which is just corresponds to these numbers, if that bit is a 1 and we don't do anything of 0. So what does that remind you of? It's basically it's literally what we said before with the V. So we have some phase and we add it if some qubit is 1 and we don't if it's 0. What is that? Okay, well, no, it is controlled, but this isn't a gate, so not exactly. It's it's a controlled thing that'll apply this phase to the 1 state if it's 1. So, huh? No. It's different. We'll define what it is. Yeah. It's not called. Yeah, pretty yeah. So again, controlled operation should ring that bell. But remember, we're only adding that phase to the 1 state, so we don't care about the 0 state. And you can actually think of it like almost like a Z gate, because Z times 0 is 0, and then Z times 1 is -1. So we're doing something to 1 and we're not doing something to 0. So this is going to be way different than just adding a negative sign. So yeah. So it's actually going to be, you good? Okay. Huh? Oh, it's called Euler's identity in general. It's just should I explain it? So if you just think of like a complex plane, if you rotate pi, this is -1, this is 1, this is I, and this is -I. So if you rotate pi, you could just think of it that gets you to -1. If you were to rotate pi over 2, you would get to I. If you were to rotate to 3 pi over 2, you would get -I. If you were to rotate by 0 or 2 pi, then you would get back to 1. So just think of it like that. But you can expand as sines and cosines if you want. Yeah. But this is like the general, this is what like a lot of people call Euler's identity. Okay. So let's figure out how we add these phases based on the states. Here's the gate. It's a diagonal gate, and it's diagonal because we're keeping the 0 and 1 states the same, but we're just adding phase to the 1 state. So this is the phase that we add to the 0 state. This is the phase that we add to the 1 state. So this is just the definition. We call it R subscript phi, and then it's this non-trivial element is e to the 2 pi I. That's like directly related to the phase here. We have e to the 2 pi I over 2 to the power of something. So yeah. Oh man, these slides take forever to load. Proof. You just do the cases of 0 and 1. Yeah, we just prove it. If we apply this R on 0, we get the 0 state. If we apply this R on 1, we get the 1 state back with its phase. So it's just doing matrix multiplication. You believe me on that? All right, nice. And remember again, that's all we need to know because if we're to apply it on some superposition, we can use linearity. Yeah. And then, yeah, you can do linearity on the gate. It's a quantum gate. It's completely reversible and everything. Okay.
even after you
Yeah. The thing is, I'm showing you like two different. I'm showing you Q of T. I'm showing you phase estimation. Those are like two separate things.
right now. It just takes a bit of time
Yeah.
just like looking at it.
My brain is not in the right state right now. I'm thinking about what my dinner
Yeah. Okay, let's finish up. So feel free to look at these. I think these go over it pretty well. So please do look at them after. Okay, we have this is our Q alpha, simplified Q alpha. This is our phase gate. Yeah, the goal is to get from some J alpha, which is either 0 or 1, because it's the bits of theta, to Q alpha. That's what we say Q of T should do. So we're gonna do something weird as if we haven't already. So we're gonna, instead of going from J alpha to Q alpha, we're gonna go from J of something else to Q alpha, and then we're gonna swap it. Or sorry, we're gonna go from J of alpha to Q of something else. And then we're gonna swap that Q of something else into the Q alpha register. So yeah, just bear with that. So uh so we're starting on this weird index right here. So we're gonna apply a Hadamard gate onto it, and the general form of a Hadamard gate is you add a -1 if that bit or if that whatever's in the ket is a 1 and you don't otherwise. And we can expand that -1 as e to the pi I, which is what I just told you. And then we're gonna add 2 in the numerator and divide by 2, just to match the form that we always have. So this is exactly this. You see that? So applying the Hadamard gate, we've added our first phase. You guys see that? So just some manipulation, we've added our first phase. Now we have to add all these other phases. So yeah, that's why we chose that weird index qubit. Um, yeah, next thing we do to apply all the phases is we just apply control of these phase gates. So it's going to be controlled on this qubit, and it's going to be add that phase if it's 1 or 0 otherwise. So these are just the indices. You can convince yourself why these are the indices, but then in the end, you will. Oh wait. Oh wait, that was right. Okay, in the end, okay, like we said, we apply the Hadamard gate, which applies this phase, right? We apply R2, which gets us this phase. We apply R3, which gets us this phase. And remember, it's controlled on this because the exponent there is that index. We keep going all the way to R alpha. And then what we get here is Q alpha. But this is in the wrong register. So this is state right here. We want J sub M minus alpha plus 1 to map to Q to sub M minus alpha plus 1. So we're gonna swap that Q alpha up here so that J alpha maps to Q alpha. So the swap, you don't actually have to swap, but like we want the J I's to map to Q I's. So yeah, each gate is just gonna add a phase. That's basically the big picture. And that was just one Q. That was just one Q alpha. We need to do that M more times. And this was hell to draw, but
first on the factor.
yeah. Okay, when we do this M times, this is what it looks like. And this is the QFT operation. We map JI's, QI's, and then up because we're doing those swaps at the end. But yeah, it's the same thing. Hadamard rotations all the way to some number. Hadamard rotations is some number. And then they just like the number of gates you have just decreases. So it actually ends up being quadratic number of gates proportional to how many qubits you input. I'm sorry that went so fast, but yeah. Uh, and also some texts will give you like a recursive definition of this, but they don't like show how it's like made. So this like actually shows how it's made. So I I hope that's more intuitive. Um, mm, okay, yeah, here Q of T, we'll map this J, which is M bits, into these Qs, which is that state that we got after applying V in phase estimation. So yeah, now we're remembering quantum phase estimation. So let's jump back to quantum phase estimation. This side too, we had this phi j, and then we're going to apply inverse Q of T. or well, if we know that Q of t maps J to this phi J, then we immediately know that the inverse Q of t will map phi J's into J's, which means we can just say that psi 3 has J in it. And remember what we said about J? We know J is directly related to theta.
Stuff if you get out or that's all you have to do it all.
Yeah, yeah, literally. So after you know J, you know theta. Yeah, we measure and we're done. And then, yeah, and then again, higher M means you have a better approximation for theta. But anyways, let's tie this back to Shor's. Okay, actually, no, I'm doing something else. At the beginning of the gate, we apply Hadamard gates, but let's make an observation. If we apply quantum Fourier transform on just the zero state, so when J equals 0, what we actually get is a uniform superposition, which is actually H on 0. So Q of t on zeros is actually H of zeros. So actually the circuit, yeah, I wanted to emphasize that, but this is what we actually do here. So we can actually replace that with Q of t's. So if you contrast this to the other algorithms we've done, we apply a Hadamard in 0, we apply the Oracle superposition, then we apply Hadamard to undo, and Q of t has just taken the Hadamard's place. Does that make sense? Sorry, I rushed through that, but yeah. Okay. Now let's tie this back to Shor's for once and for all. So at the end of quantum phase estimation, we get J. Then we use classical continued. Oh, no. Oh, okay. Yeah, we get theta because theta is J over 2M. And then we know that theta, we said that J over 2M is an approximation of K over R for some random K, which is, remember, because we did those sum of eigenvectors and got the one state. So, and then R is in there. So if J over 2M is approximately K over R, this is the order. This is what we care about. Remember the big pictures that we wanted order. So that's what we want. So we use continued fractions, which is classical, to get the order R out of this number. And then we classically compute our factor candidate, which is this. And if success, then Shor's is complete. If not, then you start all over again. And that should be it. Oh, okay. This is state of the art on Shor's, just with some hardware implementations. So, like we said, so number of gates is cubic, number of qubits is the same number of bits as n. That's typical. Some people have found more efficient methods to do that modular exponentiation. So you can reduce the gate count to whatever that is, and still n qubits. And using some error correction codes, you need a lot more qubits. So it's gone from n to 100 million or 10 million, and it'll take hours, and it takes a long time to run. And some circuits have factored very small numbers, and n equals 15. Some have done like 20 and like 21 and like 35, but they're very hard coded. It's like it's like the computer knows what to expect. And if you want to do this for large RSA numbers, then you need a lot of qubits and a lot of error. So while the theory is there, the hardware is not. So that's it. Okay. Anything you guys want me to go back to? You're hungry? All right. Huh? Yeah. Oh, if you still have to do continued practice. I'm kidding. You read it already?
Oh
Okay.
my god, this article is so long. Send this to my friend later.
Okay.
What's the annotations? It's just like that.
I can pause that. You want that? Yeah.
Yeah.